So today what we're doing is we are going to go through and look at our demo problems for 1D forces. So we're going to go through both of these problems together. And if you look at the problems and at our equations, guess what's coming back? Your favorite thing, kinematics. Who's excited? Man. Oh, I got a party hat. Man, somebody was excited about it. All right. So what we're going to do today is we are going to look at this first problem, and it says that little Susie holds a 145-gram baseball in her hand, and we're disregarding air resistance. So we're going to pretend that in this problem, in this world, that there is no air that is going to bother us in any of our forces. So air just doesn't exist right now. Anytime you see disregard or neglect or ignore any of those three words, really just like pretend it doesn't exist in this problem. In this world, little Susie doesn't need air. So for part A, it says we're drawing a free body diagram of a baseball sitting motionless in her hand. So when we draw free body diagrams, what is the first thing we have to draw in a free body diagram?
A square.
A square, perfect. So for A, let's all draw a square. Lovely square. And we have to draw forces to go on that square. So we have to draw those magnitudes or vectors to show magnitude and direction of these lovely forces. And so if there is a ball sitting in her hand, just like my calculator sitting in my hand, what forces are acting on it?
Normal and gravity.
The normal force and gravity. So can anybody tell me which way gravity goes?
Down.
Down. And which way does the normal force go?
Up.
Up. And the magnitude of that normal force, is it bigger, smaller, or the same as our force of gravity?
Same.
It is the same because it's motionless, which means they have balanced forces. So that motionless says that there's balanced forces here. All right. So now we have our lovely drawing of this object, this baseball in her hand. It says that Susie then throws the baseball upward with a force of 22 newtons. And they want us to calculate that ball's acceleration as it's being thrown upward from her hand. So for part B, we need to find the acceleration. So let's go through things we might know so we can identify an equation. So what do we know about this baseball?
The weight.
The weight. So not the weight, careful. Weight means force of gravity acting on that object. So we know it's
mass.
Mass. And what was its mass?
145.
145 grams. And what else might we know about this ball?
The force she throws it at.
Awesome. And that is?
22 newtons.
Wonderful. Do we have an equation we can use?
Yes, F equals ma, but you'll have to rearrange it.
All right. So before we can do that, I do want to point something out about these lovely newtons and what those newtons stand for, because it stands for kilogram meters per second squared. Does that change your opinion about anything that we have?
But need to be converted to kilogram.
Our mass needs to be converted to kilograms. So how would we do that?
Is it divide by 1,000?
It is divided by 1,000 because we have 1,000 grams for every 1 kilogram. So we get our mass to be how many kilograms?
.145.
There we go. All right. So now we can set up our equation and solve. So our force of on this ball is equal to the mass times its acceleration. So if we plug in what we know, we have 22 newtons equals our mass, which we know is 0.145 kilograms, times the acceleration. So how am I going to get my acceleration all by itself?
Dividing.
Perfect. All right, let's divide both sides by which value? The 22 or the 0.145?
0.145.
There we go. And our acceleration then equals what value?
$151.72. Do we need to do sig figs?
Do we need sig figs? You tell me, do we need sig figs for this problem?
Yeah.
Yes, we do in fact need sig figs for any time we do math and physics class. So what is our acceleration going to be?
150.
150. There we go. Any questions on 1 or 2 and how we did those? A or B, I'm sorry. All right, let's go to C. It says once the ball leaves her hand and it's at 7.1 meters per second, it continues to fly upward. Draw a free body diagram. For this one, let's draw that free body diagram. So the first thing we always do is draw that square. Now, can anybody tell me a force that is acting on this ball flying through the air?
Air resistance.
Careful.
No air resistance.
We just regarded it. Air doesn't exist for this lab.
Oh.
Ball.
Applied
Applied force. Which way would it go?
to the up.
Up. Okay. All right. Any other forces?
Gravity.
Gravity. I should ask, is gravity bigger or smaller than our applied force?
Smaller.
All right. Anything else? All right. I am going to say we're going to want to change this a little bit. And it says once the ball leaves her hand, so it's gone. It's no longer in her hand. It's just floating in the air. And it continues, and it's moving out 7.1 meters per second at this point, and it continues to fly upward. So there's one force that I don't like on this free body diagram. Does anybody have any ideas which force it would be?
Would it be force applied?
Why would it be force applied?
Because isn't it like when you apply a force, it goes like on the diagram, it would be going to the right, like on the right side.
Okay, so that's when we're moving to the right, when we apply that force and we push to the right. So that would be if the ball was being pushed rightward or pushed leftward, it would go in that direction. It is moving up and down only. So if we had an applied force, it would be going up. But Dat, what were you going to say?
The ball is on the air, has nothing like touch it. So
Exactly. So what does that mean for our applied force?
It's false.
No applied force because the ball is already moving. There's nothing pushing it to move any faster anymore. So there's no applying a force at this point. The ball is already in the air, so it's already left her hand. So it leaves her hand and now is at this meters per second. So it's gone. It's no longer in her hand. It's already in the air. So there's no forces acting, pushing it up anymore. So it already had that force. It doesn't need it anymore. So there's no applied force. It is just the force of gravity trying to pull that ball down. Is everybody okay with that? Any questions on that? So this is our free body diagram, just this FG, just that force of gravity. Part D says then determine the maximum height attained by the ball relative to Susie's hand. And we're using kinematics here. So we're bringing back those kinematics. All right. So if we do this, let's first come up with any variables that we might have. So what variables do we know?
Acceleration.
What's our acceleration?
150.
Anything else we know?
Velocity,
What does it equal?
7.1.
Is that initial or final velocity?
Initial.
All right. Anything else we know?
Gravity is negative 9.81.
Anything else we know?
Initial height?
All right.
Nah. Wait, maybe?
What is it?
0?
Okay.
Wait, but we need to count little Susie height too.
Nope.
Oh, okay.
Relative to her hand. So we don't have to worry about her height. All right. Anything else? There might be like one more thing, you know? Anybody see it? Any ideas? Let me ask you this instead then. What are we looking for?
Maximum height.
Maximum height, all right. So our final height is a question mark. So let's look at our equations. What equation do you plan on using?
The middle one?
So this one right here.
No, but we need time. Never mind.
So we don't have time. So we can't use that one. So which equation can we use then?
The last one?
This one?
Yeah.
All right. Do we have all those variables?
Oh, we need final velocity.
Do we have our final velocity?
No.
Is anybody sure? Anybody unsure? Or anybody positive we have that? And anybody want to tell me what that final velocity is? Because it does exist.
Oh, 0.
It does exist at 0. Why is it 0, Dad?
Because it's on top and it stops for like a little bit and fall down.
Exactly. So as it goes up to its final or maximum height, it's going to stop. It's going to turn around and come in the opposite direction. So at the very top, it does in fact equal 0. So now which equation we can use? That v squared equals v naught squared plus 2a y minus y naught. All right. So what is my final velocity again? What am I plugging in for v?
0.
Equals v naught squared.
7.1.
Plus 2a. What is my a?
150.
Times y. Do we know why?
No.
No. Minus y naught, which is?
0.
Is everybody okay with what we've written so far? Anybody not okay with what we've written so far? Anybody want to change anything?
We good. I'm good.
Everybody's saying we're good? Oh no. My next question then. All right, I've seen a lot of thumbs up and I'm liking that except for one thing. When we calculated this acceleration over here, that was because we've applied that force to get the object to move up with a force of 22 newtons. we're no longer applying a force here to get that 22 newtons. So that acceleration from before is not going to be helpful to us. What force is the force acting on this object?
Gravity, which is negative 9.81.
Exactly. Our only acceleration in this case is going to be that negative 9.81. This force acceleration is not going to be helpful because the only force we have is gravity. So the only acceleration happening is gravity's at this point. So we are going to replace this 150 with gravity's value of negative 9.81. Now we can finish solving. So what do I do next?
You square 7.1, which is 50.14.
Plus 2 times negative 9.81.
Negative 19.62.
Times y. What do I do next?
Subtract 50.14 from both sides.
And then what?
Divide by 19.62.
All right. And if I divide by 19.62, I get y equals what value?
.6.
All right. Any questions on this problem? Problem 1. All right. So then problem 2 is going to be a little bit different because now we're going to talk about 4 forces or more forces acting on our object than just the 2, the normal force and gravity, or just the 1 when we do gravity by itself. So we have to do a little bit more with this next problem. So when we look at this one, it says the purple playground rhinoceros is driving his 18,037 kilogram rocket car. From rest, he can achieve a velocity of 450 meters per second in 13.2 seconds before running out of fuel at 15 seconds. Assume the acceleration was constant, calculate it. As we're going to use kinematics because it's never going to go away. So who can tell me information that we know about this purple playground rhinoceros driving his car?
Final velocity,
All right.
which is 450.
What else do we know?
Time, which is 13.2.
Anything else?
How about 15? Well, do we have to subtract them?
Nope. That's just telling us he runs out of fuel at 15 seconds.
Okay.
So that actually doesn't affect us at all. Good question.
And initial velocity, which is 0.
And where did you get that 0 from?
Because it says he started from rest.
Exactly. He started from rest, which means that he is not moving at the beginning or his initial velocity is 0. What equation are we going to use?
V equals V initial plus AT.
All right. So if we plug everything in, we have 450 equals 0 plus A times 13.2. What do I do next?
Get rid of 0.
Get rid of 0. Now what?
Subtract. Divide by 13.2.
And I get my acceleration to equal what value?
34. Is there 3 significant figures?
It is 3 significant figures because that lovely decimal point.
Then 34.1.
Any questions on part A? All right, so then it says for part B, assuming that the mass of the car is constant, which is totally not true, but let's avoid the calculus here. It says, what is the magnitude of the net force exerted by the car by the rocket exhaust? So first, I really just want to talk about the reason why that mass is technically not true. And it's because of the fuel inside that car. When the fuel gets burned up, it gets used, it goes away, it loses its mass because it turns into exhaust and is expelled from the car, which means that there's less mass technically as we continue driving because our fuel is decreasing. We're ignoring that because it's a lot more calculations we'd have to do that we don't need to be doing here. So we're just pretending that the mass does in fact stay constant here. So it says, what's the magnitude of the net force? Now, net force really just means the sum of all our forces. So the sum of our forces here. And so we're looking for the sum of our forces as the car moves. So the sum of our forces for part B, that equation is going to be that sigma F equals ma. This sigma F stands for the sum of our forces. So when we're looking for multiple forces that we're adding together or taking away from, we're using that sigma F standing for the sum of those forces. So do I have enough information to find the sum of my forces here?
Yes.
All right. So I know my mass. What is my mass?
18,037.
And do I know my acceleration?
34.1.
All right. So now I am solving for this force. I have my sum of my forces equals my mass of 18,037 kilograms times 34.1 meters per second squared. And my sum of my forces then equals what value?
61,500 if you do sig fig.
61,552.
But the sig fig does count, right?
Sig figs count.
But how many sig fig are there? 3?
You tell me. Does everybody agree with this value? Is it improper sig figs?
Shouldn't it be 615,061?
Is that correct? And improper sig figs?
And
615,000.
There we go. The sum of our forces is 615,000 newtons. Any questions on that, ladies and gentlemen? All right, so now let's talk about our lovely free body diagram for this scenario. And then we also need to calculate the net forces in the X direction and the Y direction, including a single retarding force to account for all sources of friction. All right, so part C. Free body diagram. Who can tell me a force acting on this object?
Friction
Friction. Which way is friction going?
to the left.
All right. Friction to the left. What other forces?
Gravity and normal.
Gravity. Which way is gravity going?
Down.
Down. Wonderful. And the normal force, is that bigger, smaller, or the same length as gravity?
The same.
The same length. Perfect. And anything else?
Wait, the car's moving, right?
The car is moving.
So apply force,
Applied force, is that bigger, smaller, the same length as friction?
bigger,
Bigger than friction. And which way is it going? I'm sorry.
right?
To the right. Perfect. All right. Our applied force. Any other forces acting on this car? All right. So then it wants us to sum our forces together. So we need to find our sum of the forces in the x direction and the sum of the forces in the y direction. Which one do we want to do first, x or y?
X.
All right, let's pick our x direction. So which way is this object or this car moving? Left or the right?
Right.
To the right. So we're going to accelerate this way, just so we remember that. And if we're accelerating that way, we have our first force. Which force are we going to talk about first in the x direction?
Apply,
F applied. All right, our applied force. And what's the other force in the x direction we have?
Friction.
Friction. Awesome. And so now, are we going to add these two together? Or are we subtracting them?
add them.
Careful. So
Oh,
I like the idea, except for the fact that friction is going in the opposite direction of our motion or our movement. So we're moving to the right. Friction is trying to go left, which means friction is going to slow us down. We're going to take away some of the force we're using to go forward. So we're actually going to subtract them because they're going in opposite directions. When we add forces together, it's only because they're going in the same direction. We subtract forces going in the opposite directions. The positive one is always the one that's towards our motion. So if we're moving to the right, our force applied needs to be the one that's positive. All right, so then we actually know our total force moving in the x direction. What is that force going to equal?
615,000.
Perfect. Let's talk about our y direction. What is the force in our y direction going to equal then? What do we think?
how do you get that 6,150?
Because we learned in part B that assuming the mass of the car is constant, what's the magnitude of the net force exerted by the car? So the net force is the sum of the forces exerted by the car. And since the car is moving to the right, it's only the forces in the x direction. So our sum of our forces has to equal this. And that sum of our forces is only talking about the x direction, which means that it equals 615,000. So now what about our y direction? What are we going to use for our y direction? What forces?
The normal and gravity.
All right, our normal and gravity forces. Perfect.
Wait, so is it 0? Because normal and gravity are the same, so they cancel out.
Awesome. So our forces are 0 because they're the same, which means that are we adding them or subtracting them?
Subtract.
We're subtracting these as well because they're the exact same. And so it's 0 newtons because There's no acceleration in the y direction. All right. Any other questions on part C? All right, then we have one more question that says the rocket is known to generate a thrust of 623 kilonewtons of force. Calculate the magnitude of friction. So that thrust, what force do we think is that thrust is going to be used for? Is thrust going to be our normal force, our force applied, our gravitational force, or our force of friction?
Applied.
Thrust is going to be our applied force. Perfect. So thrust is that applied force, which means that this applied force is equal to 623 kilonewtons. It says calculate our magnitude of friction, so our frictional force. How are we going to do that?
We have to convert kilonewton to newton first.
We do need to convert kilonewtons to newtons. So how are we going to do that?
Times 1,000.
Multiply it by 1,000, so 623,000 newtons. And how are we going to find our frictional force?
615,000 equal the parenthesis minus force friction. We just plug them in.
Exactly. We're going to use this one right here because we know our sum of our forces in the x direction is our applied minus our force of friction. If we know the sum of our forces in the x direction and we know our applied force, we can then solve for our force of friction. So for part D, we're going to do our 600, our F, our sum of our forces in the x direction equals our applied force minus our force of friction. So we do our 615,000 newtons equals that 623,000 newtons minus our force of friction. And how am I going to get my frictional force by itself?
By subtracting the 623 from both sides.
Right. And if I do that, what do I get on my left side?
Negative 8,000.
All right. So my frictional force then equals what?
Don't you have to divide both sides by -1?
Exactly. Perfect. So then we have our force of friction equals what value?
8,000.
8,000. Perfect.
Oh,
Any questions on anything from this problem or problem?
is the unit is N, right? Newton?
N.